organizers for inviting me to speak. It's been a lovely week. Lots of people talking about my favorite types of groups, which is always fun. Okay, so for us, what we're going to start with is by fixing a group gamma. And you should think of gamma here as being your favorite group. This is the thing you want to understand. And some other finitely generated group, G. Right? And G is something that may vary over, you want to think of as varying over, you can plug in sort of any finitely generated group here. And our goal is to try to understand homomorphisms from G to gamma. Right, so gamma is your favorite group. You want to understand how other groups can map into gamma. This is something you can actually think about in algebra, also in topology. Gamma is the fundamental group of your favorite three manifold. You might want to know how surfaces map into your three manifold, or how other manifolds can map to your three manifold. If gamma is the mapping class group, and G is the fundamental group of some base space B, then these homomorphisms classify surface bundles with that base space, right? Another reason you might want to try to understand this set. And then there's another perspective on this, which I want to give next, where you can think about this set not just in terms of topology or algebra, but in a much more setting of like logic and equations. So I want to sort of define a way to think of this in terms of equations. And then it's very useful to sort of go back and forth between these two different perspectives. Okay, so what do I mean by an equation? So let's fix some variables. Say x1 to xn, which I'm going to think of as variables. So an equation I'm really just going to think of this as some word in these variables, right? So I can compose these variables, group operation in some way, and I'm really going to think of that as some word in the free group on x1 to xn. So x1 to xn are variables. An equation is just a word in that free group. And a solution to this equation in my favorite group gamma is going to be just a couple of elements of gamma such that if I take W, and what I mean here is every time you see an xi in W, you replace it with gi, and then you evaluate this, you get some element of the group gamma. I have a solution if that's the identity in the group gamma. Right? So this is a fairly natural thing. And if I have R, some subset of free group on these variables, I'm going to think of this as being a system of equations. And if you have a system of equations, you can look at the tuples in your group that are simultaneous solutions to all of these equations. What you get is an algebraic set. Just by definition, this is what it means to be an algebraic set in a group, right? You're the set of solutions to some system of equations. This is some tuple in gamma to the n, such that W of G1 to Gn is the identity in gamma for every equation in my system. So a priori, you can first write this down. You get a notion of algebraic sets. You can, if you want to start building up translating classical notions in algebraic geometry to the group theoretic world. You get what's called algebraic geometry over groups. This was, I think, really started by Boumslaw, Myasnikov, and Remezlnikov. Right. And this is, what?
We do have some people in the audience who can pronounce the name.
Yeah, and what you get is very closely tied to logic. Right, so there's a lot of applications there. You want to understand things like elementary theory. You start bringing together equations with quantifiers. You get all this stuff that happens in logic. These things look very different at first, but there are really two ways to look at exactly the same thing. Is if I have R, some system of equations, then I can take the group G, as given by the presentation, corresponding to the system of equations, and then there's the natural correspondence between solutions to this system and homomorphisms from G to gamma. Right, just coming from the fact that if I have a solution over here, that's a solution if and only if I can take the map that sends xi to gi, and that extends to a homomorphism. Right, so if you tell me where to send the generators, and then when I send those generators in, it forces all the relations to map in trivially, that gives me a homomorphism into my group. So solutions to systems of equations naturally correspond to homomorphisms, and I'm always going to think of only finitely many variables or just finitely generated groups. So both sides of this come up, really kind of in different ways, and then when you want to understand it, it's often helpful to look at both sides of this. So you get sort of different perspectives by looking at both sides, and I'm going to go back and forth a little bit today. So I'm going to start over here. So in algebraic geometry, one of the first things you need if you really want to start doing anything is what's called the Hilbert basis theorem. So the Hilbert basis theorem tells you that if you have an algebraic set, so in the classical setting where you look at polynomials over fields, Hilbert basis theorem tells you that algebraic sets are always defined by finitely many polynomials. And if you have infinitely many polynomials, look at their solutions. There's finitely many polynomials, and it's the same set of solutions. So in the group theory world, this is not true. This does not hold. I'll give you some examples of this later. So if we can't have a theorem, instead we can have a definition. Maybe it doesn't hold for all groups, but maybe it holds for some groups. Right, so that's what we're going to do. So a group gamma is called equationally Noetherian. If for all systems of equations, there exists some finite subset with the same set of solutions. Right, so this is really, if you want to have any hope of explicitly calculating something like this is a property that you sort of need to have for your group. Things are going to get very difficult very quickly if you don't have this. So what are groups that are equationally Noetherian? So let me start with some examples. So first one I want to say, I guess is linear groups. and this is essentially Hilbert. I mean, this is a fairly easy consequence of the Hilbert basis theorem.
Just like that,
Yes. A consequence of this, which I'm going to put on the list because, for historical reasons, is free groups. So this was first done by Guba, and the reason I put this is I think this is the first time this was ever written down in a purely group theoretic context. Since we came up with this term, he showed that free groups are equations of theory. Of course, what he did is he did the standard embedding SL2Z and then applied the Hilbert basis theorem. So, of course, really just a consequence of linear groups. Once you leave linear group world, it gets harder to find them. There are some that exist in the solvable group world. So free solvable groups. So this is a result of Gupta and Romanovsky. And really, okay, they prove something a little more general here. They have a more general class. They're all solvable groups that they prove them for. The easiest way to say it is free solvable groups. They have some more general result about these products that you can build some of these things with. Then the direction that I'm more interested in is going to torsion-free hyperbolic groups. So this is done by Salah, and if you want to remove the word torsion-free here, that's okay, but then you have to add the names Reinfeld and Weidman here. And there, I mean, their proof is really based on working out technical details, using Salah's proof and just dealing with all of the technical details that arise from torsion, which turn out to be quite a lot. In fact, all of the next results I'm going to apply are really based on the methods that Salah developed in doing this for torsion-free hyperbolic groups. So he really built a lot of the tools that are going to come up for the other examples, and then also for what I'm going to be doing later on. So oral relatively hyperbolic groups. This is done by Daniel Gross. So toral relatively hyperbolic, I mean both torsion-free and all parabolic subgroups are abelian. And then also three products of equation Noetherian groups. And so this was also done by Salah.
You going to mention any non-examples?
Yes, I am. Great question. So that's next. Okay, so to do a non-example, we need a property that equation Noetherian groups have, so we can find something that doesn't have that property. So let me list that over here. Mention maybe two things. So proposition, and this will be, I'll give another definition of equation Noetherian later, and this will hopefully be obvious then. Every equation Noetherian group is Hopfian. Okay, so i.e. what this means is every surjective homomorphism is injective. So the group is not a proper quotient of itself. So our first non-example example of a non-Hopfian group is BS23, longest log solitary group. Right, so this group is not equationally Noetherian. Or it's also fairly straightforward consequence of the definition. The group is equationally Noetherian, every subgroup is equationally Noetherian. So in particular, any group that contains BS23 is not equationally Noetherian. Right? This is, so the first group that torsion-free hyperbolic groups are Hopfian, which is also hard and not good at all in this group, but a little more work also gives you this stronger property of being equationally Noetherian. Well, before I say this, let me state our first. So our goal, that what Daniel and I started out by trying to do is to take these methods and look at what we could do with these types of things in the space cylinder, the hyperbolic world, right, and see how far we could get. So there's some obvious restrictions. As I said, you have BS23 is not equationally Noetherian. Also, BS23 star Z is not equationally Noetherian, but it is acylindric hyperbolic and even relatively hyperbolic. So you have to have some additional, you need to know something else about your group to hope to say something in the acylindric hyperbolic way. So we have some results of that. I'll mention them a little later. But let me first give our application that we can add to this list. So this is gross and stuff. If G is hyperbolic relative to equationally Noetherian subgroups, then G itself is equationally Noetherian. Okay, so that's generalizes, I guess, all three of these fall under that category. These are all three hyperbolic relative to equationally Noetherian things. This condition of requiring the parabolics to be equationally Noetherian is clearly necessary because subgroups of equationally Noetherian things are equationally Noetherian. It's also interesting that, so Solo's theorem that torsion-free hyperbolic groups are Hopfian, this is kind of hard to generalize to the relatively hyperbolic world because subgroups of Hopfian groups don't have to be Hopfian. It's sort of a little bit less obvious what you do. But when you strengthen this property a little bit, then you do get this generalization to the relatively hyperbolic world. Okay. Oh, and I should also mention there's a similar theorem in progress by Ina Bumajin and Nick Shuikin. So I'll put their names here. This theorem is better than their theorem. But they have other results that are better than our other results, which I'm not talking about today. So they have this theorem if you're hyperbolic relative to equationally Noetherian cylinder subgroups. They can prove this. And then they get some stronger results in another part of this project that I'm not talking about. So their paper is not just subsumed by ours.
So the complete project equals now the
Yes, that's here. Yes. Okay. So in order to talk about this a little bit more and to try to give the acylindrical hyperbolicity criteria that we have, I want to restate this notion of being equationally Noetherian in terms of thinking about homomorphisms, which is actually the way I like to think about it, because I like homomorphisms better than equations. So let's think for a minute about what it means to not be equationally Noetherian. So if you're not equationally Noetherian, you've got a system of equations that is not the same as any finite subsystem. That means sort of as you add equations to your list, at each step, you have some solution, which is a solution to the first n equations, but not a solution when you add the n plus first. And each time you add a new solution, or a new equation, you sort of have fewer solutions. So somehow when you translate this into the homomorphism language, it should have to do with some sequence of homomorphisms. Because something happens when you have sequences of solutions of things. So let me say what that is. So this is equation of theory in a hum in the setting of homomorphisms. You know that phi I, some sequence of homomorphisms from G to gamma. Now, the way that this is normally done is by, you say the phrase, something holds after passing to a subsequence about every third sentence. I prefer to avoid that by using a non-principal ultrafilter, which Brian was kind enough to define for us this morning. So omega is going to be a non-principal ultrafilter. You can do all of this without ultrafilters. You just it's more cumbersome. You require more words. So I'm going to avoid doing that. The stable kernel, or maybe the omega stable kernel, if you want to reference the ultrafilter of this sequence of homomorphisms, you should think about these are the things that are eventually mapping in trivially. And eventually here means with respect to the ultrafilter. So this is a set of elements in G, such that phi I of G equal to 1 almost always. As I usually say, omega almost surely. So there's an omega large set of indices where this is mapping in trivially all the time on that large set. So this is a normal subgroup, so you can take the quotient. And this is what's called a gamma limit group. Okay, so you may have heard Martin Bryson, I think, on day 1. He referenced the class of limit groups. I don't think we've heard about them since. But so classically, limit groups are exactly what you get here with gamma being a free group. So if gamma is a free group, then a gamma limit group is just a limit group. So it's generalizing exactly that notion where we put a larger class of groups here. And I denote there's this first natural quotient map from G to L, which I denote by phi sub infinity. All this is in the map. Okay, so now we have some notation. So I can state what it means to be equation no theory in terms of homomorphisms. And I'll state this as a lemma. This is well known. I mean, I've talked to other people who clearly know this is true, but I'm not aware that this is actually written down anywhere. It's not hard, it's a simple exercise. So gamma is equation in a theory if and only if for all finitely generated groups G and for all sequences of homomorphisms you get this picture. So you have G mapping to gamma by phi I. G is mapping to the corresponding limit group corresponding to the sequence. And for this, the equation of theory, it means these maps always factor through. There always exists a map like this in the diagram to use. So phi I factors through phi sub infinity. After passing to a subsequence or without sort of say that almost sure. And of course, you can't guarantee every map does this, but you can always find a subsequence and pass it. Okay. So why do I like this better? Well, I'll tell you how I like this better. So remember, gamma is going to be our favorite group. So if you're like me, whatever your favorite group is, gamma admits some type of acylindrical action on a delta hyperbolic space. Okay. So what this means is you have this sequence of homomorphisms, phi I to G. So this sequence of homomorphisms now induces a sequence of actions of G on this delta hyperbolic space. Right. So this sequence of actions, well, it's reasonably nice. It's not exactly acylindrical, because these actions might have large kernels, right? If you have an infinite kernel, of course, you fix points that are far apart. But it's sort of, it's acylindrical mod this kernel, right? You mod out by the kernel, you're getting something active acylindrical. Okay, so in order to state our result, we want a notion of, what are good sequences with respect to this action. So of course, these sequences might just be mapping into some elliptic subgroup, and then we can't say anything. So let's define what we want for good sequences. So we're going to denote by this. This is what's called the stretching factor of our homomorphism. And I want to know how far it moves points in my space, or how far the generators move points. We have the distance from x to phi I x acting on x. So my G here is generated by some finite set. Right, and I'm denoting the stretch factor